The Python skills I needed before machine learning. So everyone wants to learn AI and machine learning because of the money and all the hype. But my first AI job was building prediction models for the stock market. I was not making the next ChatGPT. I was basically cleaning data, writing Python scripts, and trying to make sense of messy financial data sets. Basically just cleaning it. There's a lot of boring work that I had to do. So here are the exact Python skills that I actually needed, right? The ones that actually mattered, right? And the ones that actually made real money then when basically the money was on the line and not just tutorials where you're actually asked to produce something and get a result. So I want to be clear. My reality, it took me 3 to 4 months to get a job, basically in web development, and then another 3 to 4 months to learn AI and machine learning. And that was a completely different beast altogether. Not many people know about this, right? But when I first started to learn Python, I actually gave up, right? So now I have like Apple, Meta, Netflix, like the FANG companies, they reach out and they headhunt me, even though I don't apply. But literally when I started, I did stop because no joke, I couldn't get it. I made so many mistakes. I think this language was the first one where I dealt with where the white spaces mattered. So if you didn't have them aligned, it would never compile. I didn't get that. I didn't know what it was doing at the time. I was making a lot of mistakes. A lot of simple things now, because again, come from experience, but there, I just couldn't even get it to work, right? And no joke, I really thought I was not smart enough. And even when I first started, I did take some coding classes. I was the only person in the class that never did coding before. And I really felt like way behind from everyone else. So I just felt like I wasn't smart enough because the concepts were just way beyond me at the time. So you might be wondering, well, how did I learn it the second time? And you want to know the reality is, I literally had no choice whatsoever for that because I had to learn this to survive in my field. It's basically learn it or I will not make it at all. That's the reality of it, right? Period. If I don't learn this stuff, I would not be able to do what I need to do. So I was forced to learn it. And you'll find that's a great motivation, like it is desperation, either do it or it won't happen at all. You'll see your focus becomes a lot more, I guess, dialed in when it's kind of like you're in a do or die type situation. Here's the thing, right? I never officially learned it from a course or a book. I learned what was needed to get the job done over here, right? I literally did not understand. Literally, I did not understand what I was doing in Python for months. Even like a year or two afterwards, I didn't fully get everything what the syntax was doing. Back then, you would go in and search for forums and look up, hey, how do you do this certain thing? You'll take it. And it kind of did what you have to do and try to change 1 or 2 variables, and it worked. I have literally worked in languages that I, to this day, had never understood what it did. I just kind of hacked together what worked. Probably now I'll understand it better, but at the time, really didn't have to do it. But the thing is, over time, I encountered so many scenarios that I basically picked it up. I learned what I need to do, and I really do believe in real life, in real production, in real job scenarios, learning just in time basically is a very vital skill that you should have to learn, right? Like, think about this, right? Infants, they're not born and then go to language school, like to, let's say, learn English if that's their native tongue, right? To learn how to speak. They're put in scenarios, and just being in the environment, they kind of pick up. And if you're in it long enough, you kind of pick up and understand the context of it, right? The thing is, that's kind of like how I learn. And now you might be saying, like, if you kind of learn that way, you will encounter people that will be saying to you, they look at your, let's say, your code or what you've done, and you see, if I did this, I would have done it this way, right? My opinion on that, I would say, is that my non-optimal solution gets the job done, right? Your perfect optimal solution is non-existent, right? So which one of us do you think a company will hire, right? So that's what it basically comes down to. What actually gets the job done? Everyone, hindsight is 20/20. Everyone's a critic. They'll tell you what should be and what shouldn't be, shoulda, coulda, would is, right? We measure things on reality and what actually works. And until you've done something, it doesn't exist. It doesn't really count. So now actually doing this for years and actually building out real software that solve real company problem and got results. Let me tell you what actually matters, right? When I was building models for the stock market predictions, this is what I actually use every single day. So one, functions and classes, right? So that's everything in production is like object oriented, at least a lot of things. There's other different paradigms, you know, if you're doing functional programming and other styles and whatnot, but functions and classes is a classic way, and you should learn how to use them. If you're using Python, learn list comprehensions. They're faster than loops, they're cleaner code. In fact, even other languages started taking concepts from that are similar that they didn't have before, right? Error handling. Basically, here your code will break and with real data. So how do you handle the error? Or exception handling, meaning something that happens that you didn't expect. That's an exception. How do you deal with that? It's not necessarily always an error, right? It could be an error, but it could be like, okay, this is an exception. Especially if you're dealing, let's say, with a video game. You might, certain things, you don't want it to crash out or stop the game. You might want it to end silently or just disable a feature. So an exception will happen. How do you want to handle it gracefully instead of just crashing, right? And then this one's really important. No matter what you do, you should learn file I/O. I/O means input and output. How do you save files and how do you read them or serialize them or deserialize them? And you want the couple of things that nowadays are kind of like standard and no matter what you do in programming. Reading CSV, that stands for comma separated values. This is actually comma separated, where you have one thing separated by a comma, another thing right here. Why that's important? Because you can read that data in, and then that could go into, let's say, an Excel sheet, like a spreadsheet, right? JSON, that's based off of like web development, and it's a structured way of dealing with data. So it's kind of like a standardized way. So what data, how it's in a known structure. So if someone else were trying to read the file, at least the structure is known that they could extract the data out of it. Beforehand, people would just write to like a text file or an ASCII file or whatnot, or even a binary or whatnot, and put in whatever the structure they want. And it made it hard for other people to share the data because the structure wasn't standardized. So you didn't know how to parse it or how to get the data out. At least using something like JSON or XML or YAML, those are known structures of at least how to parse the data. And it's up to you how do you manipulate it afterwards. So that most of the industry starts taking kind of like standardized way of saving data. And the other thing is log constantly. In fact, when actually in production, instead of using print statements to go out, you should use like a logger, because a logger, you could basically repipe that to, let's say, a text file, so you could read the logs later. You could send it to basically like to a terminal, or you could send it somewhere else to process that information. And also you could also have different levels of severity. So you could say, okay, well, I want to be very verbose, so put it like debug mode, so I want to see everything that's happening. But let's say your production mode, you change the severity down to like lower production, so it doesn't print out every little thing that's happening. You could do that if you have a logger instead of just doing print statements. What I thought mattered, but didn't. So the thing is, Python is one of those languages that people who love Python find ways to use Python. So like they call themselves like Pythonistas, right? So you might see them use a lot of extra tools that most people don't necessarily need. And yeah, they might be cool, but I would say in production, it's better to be clear than clever. So decorators, yeah, I might have used them once or twice, and maybe I use them because of the type of scenario or because of the library I'm using. That's how they interacted with it. But in general, I don't really think of using that. Again, this is always case specific. I have worked with libraries where they heavily relied on it, but that's why. Meta classes, I don't think I've ever used them really in Python, except that I might have encountered it just to understand something, but in general, not really. And then, yeah, this I've seen, especially in older technology, like complex inheritance patterns. I would definitely say keep it simple. In fact, a lot of tools, when they say to expand, if you're going to build on top of it, expand on top of it, they try to say keep it simple. Please don't try to show how smart you are because you know all the little intricacies of the language. If nobody else can understand it or understand how it's built and the performance is not really increased, like why are you really doing that, right? It makes it harder for people to to follow. Not everyone documents correctly or make documentations at all, so nobody understands it. It's like tribal knowledge, and then it's not used anymore. So it defeats the purpose. The other thing I would say that you would need is data skills for the real job, right? Basically, machine learning, I mean, it sounds, very appealing nowadays as a buzzword. AI engineering more so now, but like machine learning itself, most of the work, I would say 80% of the work is just data work, right? 15% is just debugging, and then the actual 5% is model training. And that was so common in a lot of the, application building phase, not just machine learning, is that the actual algorithm itself might be like 1 or 2 lines, but just getting the data pipeline set up correctly so you're getting and receiving it. And then why is debugging? Because the version doesn't work anymore, the syntax change, and you spend all the time getting all that to work, then the actual work itself is just like 5%. It's so common. The other thing that I would say about data skills, if you're going to deal with Python, is learn NumPy, which is short for numerical Python. If back in the day you ever worked, when I say back in the day, like 20 years ago, I would say 20, 30 years ago, there was, there still is, a math software that's used in academia called Matplotlib. And I remember using that. That was to do for doing calculus or a lot of like heavy computational math. You'd use that software so that you could actually graph things out as well. It was your best friend. NumPy is basically like very similar syntax and did a lot of the things in there. And what's great about it is that Python itself, the actual language itself, is a general purpose language. It's easy to use, relatively speaking, compared to something like C or C++ or whatnot. But one of the problems or complaints about it is that it's not as fast. So if you try to do heavy basic calculations like 1 + 1 = 2, that's fine. But if you have to do, let's say, computer graphics, where there's a lot of calculations that has to be done, a lot of big data, a lot of computation has to be done in a short amount of time, you don't want to do that with Python just because it's a lot slower. However, if you need to do pure Python, you don't want to do that. But if you want to do heavy calculations, there's a Python library called NumPy, which is still the basis of almost every computation library, including like PyTorch and TensorFlow. They're on top of, and Pandas, they're on top of NumPy. And that is actually compiled in C++ or C, right? And that is actually fast under the hood. And it's your best friend when you're doing computations, and everything is based off of this. If you're going to do math in Python, you want to learn NumPy. And if you're fortunate enough, I actually have done some like computer graphics tools that honestly, most of the time I don't need to go to C or C++ because I could either use NumPy, but there's even another one even faster than that. If you're using Windows, at least at the time, I don't think they've changed it to, I have to check. I don't think they brought it on to, let's say, Mac on Metal or something like that. There's another one called CuPy, like this, which is basically NumPy. It's very similar syntax, but it uses NVIDIA GPU. So I literally had basically programs just switch it to CuPy instead of NumPy, and NumPy is already fast, and it was 1,000 times faster than that. So you might want to check that out if you're on Windows and you have NVIDIA and you know how to set all that stuff up. But NumPy itself is the main thing you want to use. So what I use daily is basically in NumPy's array reshaping, constantly changing the dimensions. So think of it this way. I'll try to simplify it because people try to understand what is shaping and what is squeezing. So imagine that you have, let's say, like a 1 by like 3. You might see that's the shape of it. So that could mean that is like, let's say, row by column. So you have 1 row like this, and it's separated by 3. So that is 1, like this is 1 by 3 here, right? But you could reshape that to say like, okay, well, I want to reshape this data to go, let's say 3 by 1, because depending on, let's say you're dealing with matrices, which is like a grid in math, and if you have more than 2 dimensions, it's called a tensor. But you might have the right data, but you have to shape it correctly for how the data is expecting it. So maybe you have it like 1 row by 3 columns, so that's 1 by 3, like your shape, but it's expecting basically 3 rows and 1 column. So you gotta reshape this so you have 3 rows now and then one column. And that is how it's reshaped. And the thing is, you can have multiple dimensions. So you could have like a 3x5 by 4 by 2. And you might say like, okay, how do you visualize that? Well, it's not necessarily one way you could think of that is that you could have like nested arrays. Like, so let's say you could have one that's, have certain values in it. And then that's within, these are separated by comments, let's say. And then this is separated from here. So that's nested. And then that could be nested. So you could have multiple dimensions that way. That's one way, like when you visualize it, you see it. So it doesn't necessarily have to like draw it in 3D like this. But this is a super fast explanation because a lot of people don't understand when they say like array reshaping. That's what that is. And sometimes you might even hear, let's say, squeeze. And I just explained that really fast if you ever worked with NumPy. And that could be where, let's think of something simple like a 3D graphic, a 3D program where you have three dimensions, X, Y, Z. But let's say you have like X, Y, and Z. But then on one of your axes, let's say it's 0 over here. And this could be like 3 and let's say 2, right? So when you do squeeze, if you're not using that dimension, it will just like get rid of it. So it will squeeze it down to any like third 0 dimensions after that, right? So you might see that. I just want to bring it up because those are concepts that are very common in NumPy, but it's not people understand it as much. And then another concept you could use in NumPy is broadcasting. So basically you do one operation, but it goes across an array. So again, if we go back to, let's say here, let's say we go by, 4 by 2 shape, right? So we have like 1, 2, 3, 4 rows, and then 2 over here. And you can have random values like this. I'm just going to pick some numbers over here, right? So the thing is, if you were to do, let's say you had like this and you did this in regular Python and you want to multiply everything by 3, you would have to do, let's say, a for loop and say 3 times 2, then 3 times 7, and then go down to the next row, 3 times 3, 3 times 5, and keep going. Broadcasting allows you to say, you can multiply this and it will automatically multiply that whole shape, everything inside there with that number. That's what broadcasting allows you to do, right? And then indexing and slicing. So let me show that here. So basically, if you have an array, I'll just go to the side here. An array is basically, think of it as a list. Let's say you have 1, 5, 3, 8. I'm just making random things. 7. It doesn't really matter the numbers. And if you want to say, like you want to index, you could say, usually index 0. Like it's actually filling up here. Let me fill that out. If you do like an index 0 starts here because it's base 0. So 0, 1, 2, 3. So if you say index 3, that will be where the number for index 3. Now, if you want to slice it, you could say out of the subset, I want to go from here. So you would slice it from, this is index 0. This is 1, 2, 3, 4. That's the positioning. So you could say I want to slice 1 inclusive, then 2, 3, and you have to say exclusive. So you go 1 to 4, and that will return to you down here basically another array or list. If it's in NumPy, it's an array, so you have like the round brackets, but you'll return these numbers 5, 3, 4 because you slice just that part of it. So you'll have 5, 3, 4. But it's a NumPy, so you would be like this with like an array type. But that's just a quick explanation of what those are, and they're really important concepts. And then you have Pandas. Basically, it's built on top of NumPy. Think of it like if you're working with Excel sheets, you could transfer the Excel sheet directly into Pandas, and you can work on tables with a more NumPy is more mathematical based on that. This uses it, but you also do things that you could do that with that you could do in Excel, like this in a spreadsheet, like merge data sets, join, concatenate, merge. Handling missing data. Like if you have something in it's NA, how do you deal with that? Time series operation, resampling, shifting, group by operations, aggregating all this data. So things you would do in a spreadsheet, you could do it efficiently with Pandas. which is built on top of NumPy, so it's pretty fast. And you could also explore your data with that. And the other thing about that is that it's very common for the data stack to use NumPy, a process like Sheets with Pandas. And older versions of Pandas used to have, let's say an Excel sheet have different pages. You used to have like 3D, what do you call it? Like data sets, data tables or whatnot. I forgot what the name they call it, like PD for it. But then they got rid of it. So you would probably make a list of those like 2D shapes in Panda now. Now, the other thing that's very common, you have NumPy, Pandas. The other thing for visualization is that you want to Matplotlib and Seaborn are two ways to take the data and visualize and make charts and all that. That's very, very like standard. That like in any data science, machine learning, deep learning, AI, these are tools that are used all the time. They're kind of expected that right? And it's not just a nice to have. It's very important because you are the person who you're hired because you're the expert of manipulating the data. You're presenting to stakeholders who's usually, let's say in my case, and the first job I had is portfolio managers. They are not data scientists. They don't care about or even know about how it works under the hood. So you have to visualize and basically give an interpretation of what that data means for people who do not understand it. So especially if they don't understand AI, they just know it's good for something. So you have to be able to do a good visualization so they understand and basically what is the worth of the your more accurate model and what it's doing. You have to be able to explain it to them, right? I spent hours explaining signal distributions, prediction, confidence, and backtesting. So over time to let them know okay, this is what is done before, this is what is done after. Here's a visualization and basically projection how it's going to go move forward. And here's my recommendation based off of the interpretation of the data. That's what you're doing. That's what a data analyst would do, right? A data scientist or someone who builds models, AI models, they'll figure out a way to calculate the stuff. A data analyst or an analyst in general will take those, basically bring out information, visualize it, and give an interpretation so stakeholders who don't know this stuff could understand it and make a decision. Now, here's the engineering part that people skip. That is the reality most of the time. And the thing I learned the hard way. In Python, one of the things I would learn, and I still do today, is I make virtual environments. And I learned this the hard way because I had to the problem is that especially if you're taking code or even a year from now, from something you've seen before, the environment which is built, what version of NumPy you use versus what version of Python, even version of Python, what version of Pandas matters. And if you try to download them and set up your system to work one way, and then you try to work on another project that you need for that same thing, try to build something else, it doesn't work because they need another version of Python and another version of NumPy. So you couldn't get it to work. But what you could do is actually create a virtual environment. So it's like a pretend environment, I guess you could say, that's inside it, and you can make its own versions of those software and make it work. So before you start, you go into that environment and then your software would run. You would always have, prior to that, you always have this, you run something and it crashes immediately, and you try to figure out what's the dependency, and you spend most of your time. And you probably hear this a lot where people say, well, it worked on my computer. Well, if you have a virtual environment, you could also give that virtual environment or explain how to build that virtual environment with instructions, and it will work for other people's computers as well. And to do this, in Python, you use something called pip over here, pip, and that is a package manager. Think of it kind of like, say, the App Store, where you would download, if you're using an App Store to download the software you need. In Python, pip is a package manager where you could download the packages you need. And the package you would need, one of them is called VNenv, which is virtual environments. And this is how you would actually set it up to create, the project _env. That's the name of the virtual environment. You could create multiple, and then the requirement files freeze. Once you install them, you could save out the exact version installations to a requirements.txt file. It doesn't actually have to be called requirements. It just saves it to a txt file. And now you can share that file to someone else or for yourself to go rebuild that environment, install everything for it to work when you go into that virtual environment. Another one that's popular for computer science with the data science stack. Instead of using pip, actually it does use it as well, is another one called, well, Anaconda. So basically what Anaconda does, if you go down and install it for Python, it installs Python for you, but also installs the current versions of all the scientific stack. What I mean by that, like NumPy, like I was mentioning earlier, Pandas, Matplotlib, Seaborn, and a bunch of other common things like Jupyter Labs or Jupyter Notebooks, and a bunch of other things that are very common, Scikit-learn, things like that, that are used for machine learning. It's already installed. It's usually pretty big, a couple of gigabytes, but everything, not only is it all already installed, it's curated, already configured that all the versions work with each other. That's another thing about it, is that even if you have, you know that, okay, if you're using Pandas, okay, it relies on NumPy, and it might rely on, like, I don't know, I think CBAT or Matplotlib or something like that, or Jupyter Lab might do that. But you have to have the right versions or else it doesn't work. So having Anaconda at least installed, you don't have to worry about that. They made sure that all of them work, at least to the best of their effort, right? And then there's also Miniconda, which is what I normally use. It's basically Anaconda, because most of them, the actual software you use, instead of using pip, is you use a software called Conda that basically manages installing the packages for you, right? Now, the difference between Miniconda and Anaconda is they both install Conda, except that this one is empty. It just gives you Python that you have in there. And usually when you have that, you would create a new virtual environment with Conda instead of pip, or instead of venv. That's how you do it. One of the ways you make virtual environments, but you could create it with Conda as well. So normally I would do, let's say, Conda, everything's empty, and every time I do a new project, I'll create a virtual environment in there. But what's inside it, you could also use pip. So if it's not in the Conda virtual environment, it allows you to use pip. And I could also make a virtual environment for what they configured for Anaconda. And I like to do that because what I found is when you're in a virtual environment and your virtual environment doesn't have a package, if your main machine has it, it will use it. And it got me, I had trouble debugging programs before because it would work on my machine. I would export out the requirement file for another machine to install it, and it wouldn't work. And that was because it was still missing some software or some packages because it was on my machine. And it does, like, if it's not in your virtual environment, it'll take it from my machine. So what I do now is that I don't install anything on my machine. It's blank. And I go into the virtual environment and build it. So if it doesn't work, I know that because my machine doesn't have it, I'm missing it. So I'm more confident that when I release the environment file or the requirements file and share it with someone else, most likely it will work. But even then, there's still other issues. Like if you build on a Windows machine and go to a Linux machine or a Mac machine, the exact versions might not be the same, but that's another thing, right? So it's always something. And the other thing you should know as well is Git. Basically, it's source control, right? Basically, it's managing your source code or the code that you write. And what happens, and I've done this for years, is that I would write code for years, and you have just one file or just a couple of files that you're working on, and now you have a feature that's working. That's great. And then after you're trying to build a new feature and you broke something, but now what you had before, it doesn't work, and now you have to debug it and spend time, and you don't know even what your change, so it's hard. What you can do with Git is you could actually save or commit your changes, and you can keep track of it. And there's a methodology called Git flow of how you actually code your work and save it. And one of the simplest ways we could say is your main software could be on main, and that's the one that gets deployed, that gets exploited, gets deployed and gets made as the real software. And then you have like a development branch. So anytime you make a new feature, you go into development, but people are using the main branch. So you make a change, commit it, make a change. And if you have a new feature, you can make another branch called a feature branch and say like, okay, I'm making a new window. You build it, and when it's created, it goes back to the dev branch. It gets QA'd, and once that's approved, then you can say, okay, I'll merge it to the main branch or go to a RC with like a release candidate or whatnot, how it's built. But the idea is that they're separate, and this allows multiple people to work on the project at the same time. So let's say one person's working on the back end for the engine of like calculating stuff. When I say an engine, is actually doing the heavy lifting, the work. And another person is, let's say, doing the front end, let's say the GUI, the graphic user interface, like all the windows and the buttons. So they can work in parallel and then merge their changes. And then once it works, then they can merge it to the main branch. So this allows for distributed development for that. Git, you should learn how to use it so you could keep track of your information. You could also upload it to GitHub so you could have access to it and share it amongst people and download it and keep track of your own archive. And this is how you would like make branches, like your main branch. You could do git develop to do your develop branch and then push it to the origin to develop, so you can push it like online and things like that. So that's how that stuff works. Another thing you're going to have to get used to is the command line. So yeah, there's fancy IDEs or integrated developer environments such as VS Code and like PyCharm if you're using Python, which is another pretty good interpreter to use. But when you're actually working and developing these things, you don't have a GUI or IDE, or you might have to go SSH into a remote server and you only have command line or a bash so you could actually train the model on GPUs. Because if you're going to be training on, let's say, on a commercial product or a commercial model at a company, most likely your GPU on your computer is not powerful enough, so you have to like go onto a server that has much more GPU compute power, but to interface with it is command line. So you're gonna have to learn how to do that. And sometimes you actually have to edit text files. So how do you edit a text file if you don't have a window to open a text file? You could do it in command line, and there's things like nano and like vim or v, where you could type it in and now you have a text editor inside the command line. It's kind of weird because you kind of have to like learn the syntax of like how to save file, how to go to edit mode and insert things and exit and all that stuff. But these are common skills you're going to have to learn. And yeah, most likely, whether you're on Windows or Mac or whatnot, you're going to have to learn some type of terminal, like bash and the syntax for that. If you're on Windows, you probably learn command line. The syntax, they do the same type of things, but their syntax is a little different. Then there's also PowerShell on Windows. And the way you make, let's say, environment variables and things like that, they all could do it, but the syntax and how you say it or the code do it is different for each one. But again, this is going to be common practice that you would have to know. So here's the thing, right? If you're going to be learning machine learning and whatnot, you're going to have to learn some math, right? Again, AI engineering now, if you're using a model that's done, already created, and you're just putting them together, you don't have to use any of the math. You don't know how it's built, but it's good to know how these things are done and build it yourself and learn it. So when you use the AI engineering, you actually understand why it's built like that and what are the things you're tweaking. So you need to, in machine learning, you have to know what gradient descent is. Like, this is basically why your model learns. You have to know what a loss function is, what you're optimizing for. Like, I could give an example of this, right? Let's say a loss function is that you're trying to optimize an analogy. Let's say you have like a bullseye here, right? So the thing is, you have no idea. Let's say you're playing darts, right? You never played darts before, so you have no idea how well, like I just draw little circles around just so you can see, right? You don't know how good you are at it. So you throw a dart, and the first time you throw it, it goes, let's say here, like this. So you're completely off. And how you know you're off? Because this is the bullseye. So you could see that the way you threw it, you're this distance off. You're like, okay, well, it's too much to the right. So I know the next time the difference is a lot. So next time you throw it, now let's say you hit the board and you're over here. You're like, okay, I did better. I realized the first time I shot, it was really far to the right. So I'm just gonna, try to do a little more to the left. You did it, but now you overshot. And now the distance is a little less. So the difference between the first time and over here, you made an adjustment. And now you're like, okay, let me do it again. Now I did it too much to the left. Now let me go a little to the right. Oh, I'm so much closer now. So the thing is, you're calibrating by doing this, right? So, and now the distance is a little less. You could think of a loss function in a high level simplified way, is that's your measurement, is that you know what the bullseye is. You don't know what your algorithm does. So you take a shot and okay, the first time you hit it here, I'm like, okay, well, where am I here versus where it's supposed to be? And that difference is the loss, right? That's the difference there, right? So he said, okay, now I'm trying to optimize to reduce this distance. So the next time I shot it here, it's less. Okay, I take that, iterate again until until you either, usually it stops at like, okay, I'll stop after 10 tries. That's your number of iterations. So how many times you try before it stops, or you say, okay, I'm good enough. If the loss function is, if I shot it and I'm like this close, I'm like, okay, this is close enough. If I'm within a threshold, I'll stop. So those are the usual stopping conditions. That's how it works. And then there's linear algebra that you need to know. Basically, what operations are happening. And linear algebra, NumPy is really good at that. It's a way of like, and why you have to like have your shapes correctly and using broadcasting, because you could, linear algebra, matrix mathematics are really helpful because you could do a lot of calculations in one shot. That's just the nature of it, right? Now, math, like I said, is uncomfortable. It might sound that is really daunting, but you don't need a PhD. You just need to know these couple of things, and you just need to know the basics and understand it and do a couple of examples, because when you actually do this in practice, unless you're going to become an AI researcher and you're building these models from scratch from the very, very beginning, you're probably never going to do this. Think of it as, you learn in school how to add, divide, subtract, and whatnot, and maybe on the basic level, even now, like how often do you really do that? You might add some money in your head or something like that. But anytime you need to do any of that stuff, you use a calculator, right? Nowadays, if you're going to actually do any of these things, they're already built into like PyTorch or TensorFlow and whatnot, unless you're building it from scratch, which is what I teach at first. I do teach it from scratch how to build it, so you understand what it is. In practice, you never build it at scratch. There's already optimized libraries, unless you're a researcher learning how to do that. So you just need to know these basic things. I already showed you like 3 of the major ones already, so you're already exposed to it. And you only really need like 1 weekend to understand it. Go on YouTube, look it up if you want. And it will save you a lot of weeks of confusion later on, because even if you're doing AI engineering, you're not actually making any of this stuff. They'll talk about these things, so at least you'll know what it is. So now I'm talking about when you first started learning, a Scikit-learn is what I would say has a lot of like machine learning algorithms that are built in already, the common stuff, and the other common like algorithm like random forest, XGBoost, simple linear regression. That is a staple in like statistical analysis, linear regression. Right? Yes, these algorithms are boring, but they do make money because in a lot of cases, these basic algorithms work and it's good enough. And they're interpretable. They're well known. These are classic algorithms before the whole AI with deep learning, neural nets were being used with a lot of things, right? And they still work. And the general rule of thumb is that before you start off in building out really complicated neural networks or deep learning models and all that, is start off with a known algorithm that's known. It's already implemented. You could use it. One, if it does the job that you need it to do, then it's good. Move on. If not, at least you have a baseline saying, okay, why it's not good and why you have to build a model that does better than that. At least you know this is what I have to beat. And not only that, even with all these with Scikit-learn, it has these concepts already built in, so you don't have to code it from scratch. You'll learn how to train, how to do a test sets, test splits, how to properly, like account for time series, like cross-validation, basically how you set up the model training, and inference. Inference is basically using the model to actually make predictions, right? And then feature scaling. This is really critical for convergence. Basically, feature scaling is the input, the things you're looking for, and scaling it is that a lot of times you want to process it so the numbers make sense, because let's say you had data and the numbers are really, really, really big. So you might be calculating really big things, but you could do things like take the data, normalize it, take the average of it, and then like scale it down so the numbers are average and small. Like, so it's the same data, but it's massaged a bit, so it's within reasonable ways to calculate and memory management and things like that. And you'll get better results in a train. It basically says critical for convergence, meaning converge to a solution, or basically the model learns to get to a solution, right? It can still do it with all the erratic data, but it's just that, just imagine that, let's say you had to pick up all your friends all over the city. You can still do it, but go everywhere. But if you told everyone to like, hey, just come together in this one area, so I know to search within here, they're all still there, But because now it's kind of like controlled, it's a lot easier to manage. Think of it that way. Now, if they're still spread out, it can still converge, but it might be a little harder, right? So that's one other thing of like when training a model, learning how to deal with that. And model evaluation matrix is not just accuracy. There's other things of like how well, your hyperparameters perform and which one performs better and things like that. So deep learning itself, when do you actually need it? When do you actually need deep learning, right? So basically learn these things that's specific to deep learning. We talk about Scikit-learn. That's like the standard when you first start out. You're building on top of that. So you learn things like the LSTMs for time series. This is like long short-term memory. And this used to be the way to actually remember things over time. And that was dominant before, up until like 2017, until the Transformers came. And I'm not talking about the Autobots and the Decepticons here. It's the Transformer model architecture is kind of like dominant now of how machine learning works. But learning the history of this will help you. Things about data loaders and for batching, checkpoints, because training takes hours. Trust me, this is one of the first things I've done when I built my models, because I made this mistake before. So basically what a checkpoint is that you have a model architecture. Those are the nodes you build. And what it's optimizing for, you have your input, and then you have the output, which is a prediction that you want based off your input. And when you're training, you're basically training the weights of each node, like how much of an influence that when you put in this data that each node would give to tweak the knobs to get the output you want, right? So that's what you're optimizing for. You're basically trying out all different values until it gives you the results, because basically a machine learning model is a universal function approximator. Basically, you see a function, there's a pattern that's happening. You don't know what that pattern is, but you have a model that could approximate it if you turn all these knobs. So the thing is, that's what you call weights. The checkpoint is that it takes hours to train if you're using GPU. It could take days to weeks. Well, actually, even with GPU, depending how big your model is nowadays. But the things, imagine that while you're training your model, your computer crashes or you lose power. So all the weights where you were at that point, you lost it if you start over, and it could take hours to start over. So basically, think of it as like, you're playing a video game and you're saving your game, you're saving the current state. So even if something fails, you could have in your code, and that's what I built in my code, is that when something fails, you could start it up again, and it will go from the last save checkpoint and continue from there, right? Very important that I highly recommend that you code that into your code. And the other thing is moving from CPU to GPU as well, moving between them. It's funny because I actually did this thing recently. It's actually important to know with it. Like GPU is usually much faster, exponentially faster. You want to train on that. But you also have to know when to trade some CPU to GPU. Sometimes when you save model weights or checkpoints and all that from GPU, it might not work on everybody because not everyone has a GPU, or even the architecture might not be available. So sometimes you want to save things on the CPU and then move it over the GPU. The other thing is it depends on the power of your GPU and your VRAM, like the RAM for the GPU. So let's say you only have 8 gigs, but the model takes about 8 gigs for it. So then start using shared memory. This is more hardware stuff you have to kind of deal with. And if your model is bigger than your VRAM, it starts using your real RAM, which the operating system uses, and it kind of it uses shared memory. They call it shared memory to go between it. One, you don't have really control of it, and two, it's really slow. So understanding okay, it might let you do overflow of data, but it's really slow. So it might affect how you design your models to make sure it stays within the memory limits of it and for the performance. So this is what actually happens in the real world, right? This is a real world pipeline. You got to collect data. You usually do it through APIs or databases or web scraping, meaning you go to the websites and just take the information that's out there. Then you go in to clean the data. One of the major things is dates, right? Dates and time, right? So a calendar date could be all numbers, and it could be month, day, year. And then somewhere else is day, month, year. And some of them, it's not all numbers. Some of them say Monday, or MON, just MON. And some of them might say Jan or January. So cleaning the data is basically taking all that information, bringing, let's say, into Pandas, and you would identify all the dates where try to figure out which one are month, day, year. And then you might decide everything's going to be numbers and it's going to be day, month, year. So you have to go in and clean the data to make sure they're all conform to that, right? And then there's feature engineering, creating signals from raw data, like going through in there and try to find like a pattern that you could use for it. And then model training. You have to, you have to design a model, but nowadays there's so many papers out there that you look at something that's very similar to what you're doing and start off with a model architecture similar to that or like around that, right? And then if you look at the inputs and look at the outputs, if it already makes sense and the model makes sense and you have your hyperparameters, all that stuff makes sense, the actual training part should be easy, right? Once you have the data's clean and you just pretty much put it in there and just wait, right? And in a case is backtesting. In my case, backtesting meaning like you look at it at historical data, things that worked in the past, and you try to put, in my case, it was dealing, let's say, with the stock market. So you're trying to predict or try to replicate how the data would be presented. And so you don't want to have it like see the future and have bias because it knows what's going to happen and try to predict it, right? So even though all the data is already done, you want to present it in a way, you have to code it so it's fed in a way that your algorithm or your model is not seeing the future and see how well it performs, right? And once it does well, then you actually deploy your model and then you monitor it, keep track of everything's working, the performance working, even over time, like other aspects may change and you want to see, does it still work? And even in real production, you have a way of taking the data, deploying it while you're still training the new model, and then swapping out the models over whatever cadence. It might be a week, every 2 weeks, or whatever. But you want to monitor that to make sure it works. And if the new model doesn't work, to fall back, things like that. For the actual real-world pipeline deployment itself, once you have a model that's made, you want to actually use it and people interact with. These are things you should learn or be aware of, like Flask and FastAPI, or making like, REST API, a way to talk to it. Docker basics for consistent environments. So we talk about making virtual environments, but having a Docker container or some type of containerization solution is that you can basically create the environment within there and then share that out. And now you could spin up that environment when you need it, do the calculations, and then tear it down at the end. And then also basic cloud like AWS, and then you have S3 for data storage for that, and then EC2 for different computes. Working with AWS, they have different tiers and different levels of knowledge, and what these things are common whether you work with AWS or Azure or Google Cloud, same type of concepts. This is a common stack, especially if you're doing web development and machine learning. You want to do the back end, have like fast APIs or Flask to do REST APIs or fast API, be able to talk to your front end, and then to create your back end, use the Docker basically environments to create your think of it as creating your environment or your machine, your build, and then taking a snapshot that you could pass that image to other people, and they just take the snapshot, build out of it, everything works, and then tear it down when they're done. And yeah, these are data, compute, and different platforms like AWS, Azure for like Microsoft Azure, and then also Google Cloud. Those are some of the major ones. And here's what I would actually say for that. Actually create projects that actually matter, right? Not just toy projects or toy things that you do in a tutorial. So you want to build something that solves real problems. And here's a secret: in your domain, you're a domain expert in something. And if you're able to apply AI in that will be your superpower. Even if I know AI, but I don't know your domain, but you know AI and you know your domain, people looking for that solution in your domain will trust you a lot more. So you want to know that. The other thing as well is the key for the actual projects, for making it work, is to use real messy data, real world data, not necessarily Kaggle data sets. When you're starting to learn, especially if you're using like Scikit-learn when you're starting out. You're just trying to go through the basics. So you have curated data that all works. They're already clean. Everything's nice. They're already gathered for you, right? So you just like, hey, get the data set. You have the data to work on it. If you're working for real, you don't have the data. You have to figure out a way to basically procure the data, get it somehow, or create it, label it, prepare it, organize it, clean it, do all that stuff. So if you're able to do it with your domain, with the real data that people are dealing with, let's say it's a POS system, like a point of sale system for a certain company. If you're able to get data that's very similar, even how do you get it? Some of it might be online. Some of it might actually be physically in the store. How are you able to gather all that data and conform all that data, let's say in a Pandas, and make sure it all works, let's say with the date, like I mentioned earlier, like some of them are work certain times. Some of them might be like all paper. How are you able to scan that or hire a team to scan it and digitize it or do data entry yourself, get it, or hire a team to actually do the data entry? Figuring out the real world problem of a company has the data, how can you actually leverage that and then make things out of it? That is a real value, a skill that people are looking for, right? The other thing about that is, again, not tutorials, but the business value. Why do they care? What is the business value? What is they're trying to solve, right? Nobody really cares like, oh, my model is like 95% accurate than this other, the state of the art. Okay, who cares? You want to say that my model saves 2 hours a day and it beats, not that it beats, 95% accuracy. It saves 2 hours per day. To a company, they're like, oh, wait, we save 2 hours a day. We do that every single day for every week, every month, every year, how much they save. That is valuable to them. And here's the truth that I would say, I would say that I feel stupid 80% of the time at the beginning, all the time, even now, right? Now the thing is, that's normal because you literally don't know anything at the beginning, right? And you have to get over that, right? Because I still feel that way sometimes, right? And even now, I built AI self-driving cars and worked for, Apple Vision Pro over here, right? Yeah, I did AI models for these things, right? But here's the thing. The path isn't just, okay, I learned Python, then I know ML, machine learning, and then I get a job. It's not that simple. First, you're like, okay, well, let me just learn Python, the basics in the first place. What is it? How do I just do basic things on it? Then let's look for real world problems and let's solve that, right? Now, how do we want to solve this real world problem? How do we actually get the data from the real world? If it's a POS system, like point of sale system, or maybe they just have like physical receipts or physical documents, how do you get that digitized? Okay, so you solve that. Then you have more real world problems where, okay, well, only this one person has that information and they're not here half the time. How do you get that? It's just weird things like that. And then you do simple ML. Like I mentioned, you can use Scikit-learn, use the basics first. Before you do something complicated, just see what the baseline is. Sometimes just a linear regression, a lot of times, is all you need. If it works, use it. K-cluster mean, something like that. Do all the stuff that works and say, okay, it's really not working. Let's do something more complicated. Then that's when you start doing deep learning and you justify it because you're like, listen, these baselines don't give us, this is what we need to do. And that's also when you would pitch to get funding to get your project off the ground. And then once you can do all these things, then you could get the job, because this is what you need to be doing for your job. And out of all that, clarity in your head beats cleverness in your code, right? As long as you understand exactly what's happening, and that's why it's very clear to have your path beforehand, your system and what you need to do. You could swap out the actual things in your code, because you could start off, let's say, with Python and you start with another language. But if you still know what you're going, your roadmap, that will make it very clear and people follow that. And understand what you're building. Main thing, why? You don't do things just for the sake of it. Understand what you're doing. Again, this goes back to here, syntax, that's code, like how to actually code it, that will come. You really want to understand what's actually happening here. And always start with a baseline. Start with something tiny, this tiny like coding script, and make it work, right? Then make it better. Once it works, then make it better. That's why I say start off with Scikit-learn. Don't necessarily start off with PyTorch or TensorFlow. Use the basic algorithm out of the box, make it work, and see how good is it. And then make it better if you need to, right? That's how you become an ML engineer. You don't try to invent problems that you just solve, right? You don't do it just by watching tutorials or, reading like some papers. You actually have to build things, because when they actually hire you, you're going to be working in the real world, and you have to have these real world problem solving skills. Your first script starts today. What problem are you going to solve?